So we have the last talk of the morning session by Abhash Kumar Jha from IIT BHU. He will be talking about certain spaces of Cusp forms spanned by eta quotients and applications.
Yeah. Okay. Thank you, Akshay, for the introduction. So let me begin by thanking the organizers for inviting me to speak in this wonderful conference. So today I'm going to speak on certain spaces of Cusp form spanned by eta quotients and its application. So let me first mention that it's not directly related to the theme of the conference, but somehow this work is motivated from a work of Gold-bach, which involves evaluating certain special values of L functions. And the goal of the talk is to study certain congruence and identities for the partition function. And the circle method, which is main theme of this conference, is kind of developed while studying the substitute formula for the partition function. So yeah, so I'll just give you the outline of my talk. So I'll just review the partition identity, which I'm interested in, and then I'll briefly review the definition and some properties of modular forms, which I'll be kind of using to prove the theorems, and mention some results and proofs. So let me start by defining partition. So what is a partition? So a partition of a natural number n is a representation of n as a sum of smaller numbers and which add up to n in a certain order. Generally, we take it to be non-increasing. So, and the number of partition of a natural number n is given by the partition function. So, for example, if I take n to be 4, then the number of partition of 4 is 5. So we can write 4 in 5 ways. So namely this, then 3 plus 1, then 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So in general, in the theory of partitions, we are kind of interested in the power series generating function of the partition function. And it is due to Euler to prove that this generating function is given by this infinite product. It is due to Euler's. So if you see, these partitions are additive objects, right? So it is very difficult to believe that they satisfy some congruences. But it was because of Ramanujan, he observed from the McMahon tables for partitions, and he first conjectured these congruences for modulus 5, 7, and 11, and he also proved it. So more precisely, these congruences are like this. So if you take 5n plus 4, p of 5n plus 4, p of 7n plus 5, and p of 11n plus 6, they are divisible by 5, 7, and 11 respectively. So, and also these have connection with modular forms. So Ramanujan congruences have connection with modular forms. So further, this Algren and Boylan, they have showed that these Ramanujan congruences exist only for these primes. So there are no other prime other than this 5, 7, and 11 for which this type of congruence holds. However, there are some prime power congruences satisfied by these partition functions, namely of this form, p of L to the power kn plus delta Lk is congruent to this modulus L to the power k, where my L is this prime, 5, 7, and 11. And this delta k is this integer with this congruence condition. So note here that in the case of 7, this modulus is not actually L to the power k, but it has to be 7 to the power this integer part of k by half plus 1. So these are some congruences satisfied by this partition function. So to prove these congruences, something called witness identities. So this is my notation, q infinity. It's like this, and from 1 to infinity, this is finite product 1 minus 2 to the power n. So Ramanujan took these two identities. So, and these two identities immediately give you this congruence modulo 5 and 7. And that's why these two identities are called witness identities, because they witness this Ramanujan congruence modulo 5 and 7. So we are interested in this type of function. Essentially, these are some modular forms. I will talk about it. These are some eta quotients. Okay. So these identities are called witness identities. But Ramanujan didn't find any witness identity for the modulus 11. Okay, and to prove this witness identity, actually Ramanujan stated these two identity, which I'm going to state now. So this is identity. So you have one side, you have a Q series. So Q to the power 5, Q to the power 5, infinity to the power 5, and denominator we have Q infinity, and right side we have this series. So basically this series, as I've told, this is kind of a modular form, and this right hand side is basically an Einstein series. So I'll talk about this later. So what you do, if you extract the multiple of Q, power of Q, which is multiple of 5, you'll get witness identity, modulo 5. In the case of 7, Ramanujan has this identity. So he expressed this kind of Einstein series in terms of linear combination of two modular forms. Okay, here also you extract the terms, which is multiple power of Q, which is multiple of 7, and you use this Jacobi identity because this QQ infinity to power 3 is appearing here, so you have to use this Jacobi identity to get the witness identity modulus 7. So these are the two witness identity which Ramanujan gave. So now what is the situation in modulus 11 case? So this was Lehner who gave this witness identity in modulus 11 case. So as you can see, 11 is here, right? So, but one has to prove that the coefficients coming from here are integer. That is not actually easy to prove. And to prove this, Lehner used the theory of modular functions. So later, Atkin also obtained a new witness identity, and this Paule Rado recently they obtained some witness identity using some Gold-bach and Ramanujan package. They gave kind of algorithm to find that. So all these approach for finding witness identity modulus 11 was using the theory of modular functions. So what we have done is we have obtained the witness identity for modulus 11 using theory of modular forms. Also, there is a theory of modular function is involved, but yes, explicitly we used this idea of Ramanujan to express certain Einstein series in terms of some nice modular form, which is eta quotient. And here, so in this case, it is one dimensional, so there are only one eta quotient here. But in this 7 case, there are 2. So we'll see things are complicated in the case of 11 because the underlying modular curve has genus 1. So if you look at the modular curve of level 5 and 7, they are genus 0. So there are sufficient eta quotient to span the space of modular form, but that not in the case of, so in level 11. So I'll first state the witness identity which we obtained. So let me define these functions, WK function. This is called Fine's WK function. And these are given by this infinite product. So this is the witness identity we obtained. So this P of 11 n plus 6 is given by this 11 times Q to the power 4, this eta quotient into this expression. And these F2, F3 are given by some expression like this. Okay, so I'll tell why these coefficients are integer. And once you have this, all these coefficients are integer, you immediately get the congruence of this Ramanujan congruence modulo 11. Essentially, you obtain this witness identity. So this is the result. Now I'd just review the theory of modular form and some basic property which I need to prove this result. Okay, so let me start. So this H will denote my upper half space. So it's a set of all complex number having positive imaginary part. And this gamma naught n is a Hecker congruence subgroup. So it is all 2 by 2 SL2Z matrices having third entry divisible by n. So I'll consider this modular form. So a meromorphic modular form of weight k over this congruence subgroup with character chi is this meromorphic function on upper half plane. It satisfies these two properties, right? So it's first transformation property like this for every this gamma naught n matrix, and it is meromorphic at all the curves. So if my weight k is 0 and chi, this character is trivial, we call this f to be modular function. And if my function f is holomorphic on the upper half plane and also on the cusp of gamma naught n, then we call this is a holomorphic modular form. And if f is a modular form such that it vanishes at all the cusps of gamma naught n, we call it a cusp form. So, and this is the notation for this space of modular form over gamma naught n with the character chi, mk and chi, and sk and chi is the subspace of cusp form inside this modular form mk and chi. Now I'm going to define a UP operator, which I will be using in the proof. So now I'll be very specific. So my label will always be the prime, and weight will always be p minus 1/2, and character will be this dot p legend, this symbol. So this will be my character. So I'm defining this UP operators. Okay, so I forgot to mention that if I have a modular form, it has a Fourier series expression like this. So if I start with a modular form f of weight p minus 1/2, label p and character chi p, then I'm defining this action of this UP operator on f as I'm just disturbing this Fourier coefficient. There should not be dot. So I'm just disturbing this Fourier coefficient. I'm just multiplying its argument by p. And it is not difficult to see that this UP operator takes modular form to modular form and cusp form to cusp form. So yeah, so this is one thing which I need. Then another thing is some Einstein series, the Einstein series which I was talking about. So I'm defining for my purpose that this is p minus 1/2, weight is p minus 1/2 on this group, and it is defined by this infinite series. So this is kind of some running over divisors of n and chi p of n over l and l to the power p minus 1 by 2 minus 1 q to the power n. So this is an element inside mp p minus 1/2 gamma naught p chi p. So now this UP operator, which I have defined in the previous slide, acts very nicely on this Einstein series. So namely, it just gives you the scalar multiple of this Einstein series, and this is also very nice. Okay. So now another thing which I need is eta quotient, which appeared in the title. So first, let me define this Dedekind eta function. So it is defined by this q to the power 1 by 4 qq infinity, and it is it satisfies very nice transformation property with respect to SL2Z. So it transforms like a modular form of weight half. Okay. Now we have this is a very general result, but I'm just stating in a very special case which I need. So this is a result of Gordon, Hughes, and Newman, and they classify when a eta product or quotient is going to be a modular form. So suppose you have this function f, which is eta tau into eta p tau with some power. So these can be negative, positive, anything. So if both of them are positive, they are eta product. If negative and positive, then they are eta quotient. So it says that this is a modular form of weight p minus 1/2 and label p with character chi p if these four conditions are satisfied. So what are these four conditions? So this R1 plus RP is p minus 1, and these two congruences should be satisfied by this R1 and RP. So R1 into P times RP is divisible by 24. P times R1 plus RP is also divisible by 24. And this inequality, R1 plus RP by P is bigger than or equals to 0. So, and if this, in this fourth inequality, if this is strict, then this F becomes a cusp form. So this is kind of characterization of eta quotient when it becomes a modular form or cusp form. So that is one thing we should. So next thing, I need this result, which says that when two modular forms are equal. So suppose you have a two modular form f and g having Fourier coefficient afn and this bgn. Then suppose if their Fourier coefficients agree for these many indices, like for all n, p square minus 1 by 24, then it says that all the Fourier coefficients are same. So essentially your modular forms are same. So this is kind of determining modular form by their Fourier coefficient. So, okay, so that is fine. Now I can give a proof, but before that, I'll just tell what basis element I'm interested in. So to define the basis element, I need some notation. So I'm defining this G. This is basically genus of that modular curve. So if G is defined by these three congruence condition, then suppose this for a prime P. Okay, so I should mention that my prime is bigger than 5 and less than or equals to 23. So I'm in this range. So I should have mentioned it. Anyway, so Fp denote the set of all modular functions f in gamma 0 p such that it has only one, it has pole only at this cusp infinity, not at 0. So gamma 0 p has two cusps, infinity and 0. So it is having only pole at this cusp, infinity, and not at 0. So we need a good basis. I'm saying it basis to be good. So you need a good basis B1, B2, BD, where D is my dimension of this corresponding cusp form. I need these two properties. This Bj should lie in this ring, so that the coefficients are integer, so that I can get the divisibility property. So if I 11 or whatever divisible I'm looking for is in the outside of that expression, then I can immediately conclude that it is divisible by that 11. And another thing, it's Q expansion starts from Q to the power J. So these two things I need. And for this, so this type of basis is given by Garvan. So Garvan gave a basis of this space, which is essentially of that type. And so this is the result of Garvan. So I have a prime P bigger than 5 and less than 23. A dimension of D is given by this Rp minus G minus 1. So here Rp is P square minus 1 by 24. And G was the genus which I have defined earlier. So then this particular set forms a linear basis of a space of cusp form of this weight P minus 1/2 on gamma naught P. And this Bj is defined something like this, depending on the this running variable J. So you see, this is product of eta quotient and some these functions, these Fi's. So these Fi's are basically the polynomial basis of Fp. Okay, so now these Fi's actually, I was talking about the work of Gold-bach. So these Fi's actually appeared in the work of Gold-bach, where he studied some partition identity as well as evaluated some special values of L functions. So this basis comes from the work of Gold-bach. Okay, so using this basis, Garvan has constructed this this basis, and we'll use this basis to prove our witness identity. Okay, so now, so I'll just recall the witness identity which we want to prove first. So this is the expression. So let us start. So consider this Einstein series which I have defined earlier. So if I take my P to be 11, I'll get E5. E5. This is Einstein series E5, and this is an element in this is a modular form of weight 5, level 11 with this character chi11. Okay. Now the theorem of Garvan gives me this basis. So for P equals to 11, this is 3-dimensional. So let us write this basis element B1, B2, and B3. Okay, where F1, F2, F3 are explicit function, and they are polynomial basis. So my claim is, so my idea is to express this Einstein series in terms of these functions. Okay, so my claim is this. So E5 can be written like this linear combination of these elements. So these are basis of cusp form. This is something else. This is not cusp form. So now, if you use the result of Gordon, Hughes, and Newman on eta quotient, where they classify that, they characterize the eta quotient, then it will tell you that this particular eta quotient satisfy all those 4 conditions, and they are an element of this space. Okay, so to check that how they are equal as an element in M511 chi11, what we can do, use the result of Buzzard, which says that you have to check only finitely many Fourier coefficients, namely 5 Fourier coefficients. First 5 Fourier coefficients are enough to check, because this 5 is P square minus 1 by 24 and with P11, and this can be verified. So we have verified it using like SAGE, but it can be verified by other method also. So now this says that you have these two modular forms. These two modular forms are same. Now what you do, you apply this U11 operator on this. So U11 operator behaves very nicely with Einstein series. So it will give U11 to the power 4 into this E5. Now you will apply U11 on the other side, And let's see what happens. So other side, we have three elements. These are elements from Cusp forms, and this is not a Cusp. So we'll evaluate U11 of this, U11 of this, U11 of this. So again, I know that my UP, this operator takes Cusp form to Cusp form. So U11, this B1 is going to be Cusp form. So I can write it as a linear combination, and then I can use the result of budget where I can compute the first 5 Fourier coefficient to determine whether this is same or not. So that's fine. So in this way, we can compute all these images of this B1, B2, and B3 under U11. Okay. Next, yeah, here one has to do some thing, but this is a routine calculation. You have to just pick this coefficient in the both side, and you'll see that U11 of this is given by P11n plus 6 Q2 to power n plus 1 multiplied by this eta tau to the power 11. This is basically eta tau. Okay, now if you put everything together, you'll get the witness identity which we have stated. So that is the idea. You just hello. Is there any question? Okay, so
you can go ahead. No questions.
Okay. So the idea is to express the Einstein series in terms of a good basis. Okay, so and we can do the similar thing for other levels. And for P equals to 7, this is not a witness identity, but yeah, these are some identity, because as it is already proved by Algan and Ball, and we have only congruences for 5, 7, and 11. So this is some kind of identity where you get, but yeah, these are all computational results. We have to, it involves a very lengthy computations. And for P equals to 19, this identity looks something like this. And also P equals to 23, it looks something like this. So this is one thing one can get using nice basis. One can get some identities for the partition function. Now, another thing is we also obtain this one. This was already obtained by Zuckerman using the theory of modular function. So if you compare all the identities, in this case, P equals to 13, this expression is very nice. Nice means all the terms are exactly eta quotients, not other like function, other basis element. So this is because of, again, this fact that this, again, genus of this underlying modular curve is 0. And there are very sufficient eta quotient to span that space. So I don't know what is exactly the relation with this eta quotient and genus of that modular curve. So yeah. So another thing, also one can apply this same technique to obtain something called expression for Ramanujan's theta function. So this was the theta function Ramanujan considered, and he claimed without proof that this satisfies this particular equation. So later, Rangachari proved the Ramanujan claim, and he also kind of evaluated certain values of Fn for 2, 3, 4, 5, and 7. Later, Algren computed for this 6, 8, 9, 10, and K-Nono for n equals to 11, and Sua for n equals to 13. And using the same technique, we also obtain this value for 17, 19, 23. And also we obtain two expressions for this F11, which was obtained by Ono, but that is actually different from Ono. So this is also one of the applications one can see. So yeah, so I think that is all I have to say. Thank you.
Thank you, Abhash. Any questions from the audience? Yeah.
Thanks, Abhash. So my question is about your theorem. So you have witness identities for P17, 19, and 23. But these huge expressions. Is there any pattern, or are these just hard computations?
No, these are computations actually. So basically the idea is same. We have to express Einstein series in terms of some nice basis elements, and then you have to do computation to show that expression is same, and that you use the result of budget that we compare. You check that first few Fourier coefficients are same, and for that we use Sage to verify that.
I see. Thank you.
Hello. Yeah. So using these identities, can you show some type of congruence? I mean, not exactly like the Ramanujan congruences, like not congruent to 0 or something, but say for example, P of 99 plus 4 is congruent to some function of n mod 90.
Yeah, that it's not obvious, but yeah, some congruence one can expect. I don't know. But yeah, but one thing I can say, all these coefficients, all these things appear inside are like integer, but I don't know where something is coming out from that or not. Like common factor is coming out, or that is not obvious. We haven't checked that actually. That something can come outside. Like you see in this case here, yeah, 11 is here. It is a factor coming from all these factors, right?
Yeah.
But it is, I don't know. We haven't checked, but I don't.
I think that is a bit too much to expect, because there is a theorem which says that such the exactly the same congruences like what Ramanujan predicted will not happen for other model. I'm asking something which is weaker, in that even if you have higher model, let's say mod 19 or 17 or something, can you write the congruence in terms of some simpler functions on the right, instead of 0 on the right hand side? Can you have some simpler function?
Okay. No, we haven't checked that. We haven't thought about that.
Okay. Thank you.
So can you show the 19 congruence once again?
Yes.
Actually,
the last two terms have a 19 in them.
Yeah, these two. No, not last two. Here also 19 is there, but there are many 19, but not everywhere. So
actually,
obviously 19 is not going to come out.
But the 13 congruence that you had, that 13 identity there, except the first term, everything was divisible by 13, except this first term.
Yes. Yeah.
So it is like almost you have something congruent to 0 mod 13, but
yes, yeah, but not exactly.
Yeah. Right. Any other comments? All right. So let's thank Abhash again for a very nice talk.